Everything we thought we knew about our place in the cosmos just shattered. In a moment that will echo through human history for millennia to come, the James Webb Space Telescope has detected something that should not exist, something that challenges every comfortable assumption we have ever made about the rarity of life in this vast, cold universe. A planet, not just any planet, a world orbiting a distant star, bearing the unmistakable signatures of life, with a probability so staggering that scientists can barely bring themselves to speak it aloud: 99.7%. 99.7%. Let that number settle into your consciousness for a moment. In the cautious, conservative world of astronomy, where researchers hesitate to claim certainty even when staring at the most obvious evidence, this figure represents something unprecedented. This isn't a maybe, this isn't a perhaps, this is as close to absolute certainty as science ever permits itself to approach. And what it tells us is this: we are not alone. But how did we arrive at this moment? How did humanity, after millennia of staring at the stars and wondering, finally stumble upon proof that life exists beyond our small blue world? The story begins not with an answer, but with a question that has haunted our species since the first human looked up at the night sky and felt that peculiar mixture of wonder and terror. Are we alone? It's such a simple question, just 3 words, yet it contains within it the entire weight of human existence, the sum total of our hopes and fears about our place in the grand scheme of things. For thousands of years, we had no way to answer it. The stars were just points of light, beautiful but inscrutable, silent witnesses to our confusion. Then came the revolution that transformed those points of light into suns, each potentially surrounded by worlds of their own. Suddenly, the universe wasn't just big, it was incomprehensibly vast, filled with billions upon billions of potential homes for life. The question shifted. It wasn't whether there might be other worlds anymore. We knew there were. The question became, how do we find them? And more crucially, how do we determine if any of them harbor life? For decades, astronomers developed theories about what life-bearing worlds might look like. These theories were built on the only example we had: Earth. Our planet became the template, the cosmic yardstick against which all other worlds would be measured. And what made Earth special? What were the ingredients in this recipe for life? Water. Liquid water flowing across a planetary surface, pooling in vast oceans, evaporating into clouds, falling as rain. Water was the first requirement, the universal solvent in which the chemistry of life could unfold. Scientists imagined it like a cosmic soup, a medium where simple molecules could meet, interact, combine, and eventually, through processes we still don't fully understand, become something more, something alive. Temperature. Not too hot, not too cold. The Goldilocks zone, they called it, borrowing from a children's fairy tale to describe something profound. A planet needed to orbit its star at just the right distance, receiving just the right amount of warmth. Too close, and any water would boil away into steam. Too far, and it would freeze into useless ice. Life needed conditions that were just right. And atmosphere. A blanket of gases to hold in the warmth, to protect fragile organic molecules from harsh radiation, to transport water vapor from the oceans to the land. Earth's atmosphere was like a protective cocoon, a thin shell of air that made the difference between a living world and a dead rock. And time. Vast stretches of time for evolution to work its slow, patient magic. Billions of years for single-celled organisms to become complex, for those complex organisms to diversify, to colonize every available niche, to transform the planet itself through their collective existence. These were the old theories, the conventional wisdom about what made a planet habitable. And they made sense. They were logical. based on sound scientific reasoning and the one data point we had. But here's the thing about theories based on a single example. They're inherently limited. It's like trying to understand all of human culture by studying one village. You might get some things right, but you're going to miss so much. For years, astronomers searched for Earth's twins. They pointed their telescopes at distant star systems looking for rocky planets in the Goldilocks zone. They found thousands of planets, a bewildering variety of worlds that defied easy categorization. Hot Jupiters orbiting impossibly close to their stars, super-Earths larger than our world but smaller than Neptune, ice giants and lava worlds, and planets where it might rain diamonds. The universe, it turned out, was far more creative than we had imagined. But finding potentially habitable planets was one thing. Proving they actually harbored life was something else entirely. How do you detect life from hundreds or thousands of light years away? You can't exactly send a probe to collect samples. The distances are too vast, the timescales too long. Even traveling at the speed of light, which nothing with mass can do, it would take years or centuries to reach these worlds. And we can't travel at the speed of light. Our fastest spacecraft would take tens of thousands of years to reach even the nearest stars. So astronomers got creative. If you can't go to the life, you find ways to detect its presence from afar. And life, it turns out, leaves signatures, fingerprints in the light. When starlight passes through a planet's atmosphere, that atmosphere absorbs certain wavelengths, creating dark lines in the spectrum. Different molecules absorb different wavelengths. By analyzing these absorption patterns, scientists can determine what gases are present in that distant atmosphere, and some gases are particularly interesting. Oxygen, for instance. Free oxygen is incredibly reactive. It wants to bond with other elements, to form oxides and peroxides. On a dead world, any free oxygen in the atmosphere would quickly disappear, locked up in rocks and minerals. The only reason Earth's atmosphere contains so much oxygen is because living things produce it constantly through photosynthesis. Trees and algae and countless microscopic organisms pump out oxygen as a waste product of their metabolism. Our atmosphere is, in a very real sense, the breath of all life on Earth. If you detected large amounts of free oxygen in an exoplanet's atmosphere, it would strongly suggest biological activity.
Methane is another biosignature. Like oxygen, methane breaks down over time when exposed to ultraviolet light. Its presence in an atmosphere means something is constantly replenishing it. On Earth, much of our atmospheric methane comes from living things. Bacteria in wetlands, in the guts of animals, in rice paddies. Methane doesn't prove life, but it's suggestive, especially in combination with other indicators. The real smoking gun would be detecting multiple biosignatures together, gases that shouldn't coexist in a lifeless atmosphere. Oxygen and methane, for instance, are chemically opposed. In the absence of life, one would quickly destroy the other. Their simultaneous presence suggests active biological processes constantly replenishing both. This was the dream: to point a telescope at a distant world, analyze its atmosphere, and find the telltale signs of life. But there was a problem, a big one. The telescopes we had weren't powerful enough. Analyzing the atmosphere of a distant planet requires incredibly precise measurements. You're looking at a tiny world, billions of miles away, trying to detect subtle variations in its already faint light. It's like trying to see a firefly next to a searchlight from 1,000 miles away. The technology simply didn't exist. Until now. The James Webb Space Telescope changed everything. Launched on Christmas Day 2021, this engineering marvel represents humanity's most sophisticated eye on the cosmos. It's not just big, it's transformative. Where the Hubble Space Telescope, its famous predecessor, could glimpse the universe in visible light and a bit of infrared, Webb operates primarily in the infrared spectrum, seeing heat rather than light. This seemingly subtle difference opens up entirely new ways of studying the cosmos. Why infrared? Because infrared light can penetrate dust clouds that block visible light, because many of the most interesting chemical signatures show up in the infrared, because infrared lets us see the universe not just as it appears, but as it truly is, revealing the heat signatures of stars being born, of planets forming, of ancient galaxies shining from the edge of the observable space and time. Webb's mirror is enormous, a collection of 18 hexagonal segments made of beryllium coated in gold, working together as a single surface 6.5 meters across. That's more than 2.5 times the diameter of Hubble's mirror, and since light-gathering power increases with the square of the diameter, Webb can collect almost 7 times more light than its predecessor. More light means better sensitivity, sharper images, the ability to see fainter, more distant objects. But the mirror is only part of the story. Webb carries an array of instruments that would make any astronomer weep with joy. Cameras that can capture images of unprecedented clarity and depth, spectrographs that can split light into its component wavelengths with exquisite precision, revealing the chemical composition of objects billions of light years away. And all of this operating at temperatures just above absolute zero, cooled by a massive sun shield the size of a tennis court, necessary because infrared observations require the instruments themselves to be colder than the objects they're observing. The telescope doesn't orbit Earth like Hubble does. Instead, it sits at a special point in space called the second Lagrange point, or L2, about 1 million miles from Earth in the direction opposite the Sun. At this location, the gravitational pulls of the Earth and Sun balance in just the right way to keep the telescope in a stable position relative to Earth, while also allowing its sun shield to block light from the Sun, Earth, and Moon simultaneously. It's a cold, dark, perfect vantage point for observing the infrared universe. When Webb became operational, astronomers had a list of targets stretching into years of observing time. There were ancient galaxies to study, stellar nurseries to examine, the atmospheres of planets within our own solar system to analyze. But high on that list were exoplanets, those distant worlds orbiting other stars. Because if any telescope could detect the subtle atmospheric signatures of life, it would be Webb. The target in question, the planet that would change everything, orbits a star designated K2-18, located about 120 light-years from Earth in the constellation Leo. The star itself is unremarkable, a red dwarf smaller and cooler than our Sun, one of billions of similar stars scattered throughout the galaxy. But this particular star had something special, a planet designated K2-18b that had been intriguing scientists since its discovery by the Kepler Space Telescope years earlier. K2-18b is what astronomers call a mini-Neptune, a category of planet that doesn't exist in our solar system. It's larger than Earth but smaller than Neptune, with a mass about 8.6 times that of our world. Previous observations had already established that it orbited within its star's habitable zone, that precious region where temperatures might allow liquid water to exist. They'd even detected water vapor in its atmosphere, a promising sign. But water vapor alone doesn't mean life. Venus has water vapor. Mars has water vapor. You need more evidence, more pieces of the puzzle fitting together. Webb turned its golden eye toward K2-18b, and what it saw changed everything. The data came back in the form of spectra, those graphs showing how much light the planet's atmosphere absorbed at different wavelengths. To most people, these graphs would look like meaningless squiggles, ups and downs on a chart. But to the trained astronomers analyzing them, these squiggles told an astonishing story. First, the water vapor signature was confirmed and strengthened. There was a lot of water vapor in this atmosphere, more than anyone had expected. But that was just the beginning. The spectra also showed methane, significant amounts of methane. And here's where it gets really interesting. They detected carbon dioxide, not just traces, but substantial quantities.
Now, carbon dioxide and methane together are already noteworthy. On Earth, this combination is maintained by biological activity. But the real bombshell came from another detection, something so unexpected that the research team spent months checking and rechecking their data, running simulations, eliminating every possible alternative explanation. Dimethyl sulfide. 3 words that sent shockwaves through the scientific community. Dimethyl sulfide, or DMS. On Earth, this molecule is produced almost exclusively by living organisms, particularly phytoplankton in the oceans. When phytoplankton break down certain organic compounds, DMS is released as a byproduct. It rises into the atmosphere where it plays a role in cloud formation. We can smell it when we visit the beach. It's part of that distinctive ocean scent. The crucial point is this. There are no known non-biological processes that produce significant amounts of DMS. None. On Earth, if you detect DMS, you're detecting the chemical signature of life. And now, for the first time in human history, we were detecting it on another world. But wait, the skeptics said, and rightly so. We can't just assume that what's true on Earth must be true everywhere. Maybe there's some geological process we don't know about that could produce DMS on this alien world. Maybe the chemistry works differently there. Science demands that we eliminate every other possibility before jumping to the conclusion of extraterrestrial life. So the scientists looked for alternatives. They ran computer models simulating every non-biological chemical process they could think of. Volcanic outgassing, photochemical reactions in the upper atmosphere, interactions between the atmosphere and the planet's surface, meteorite impacts, lightning, chemical weathering of rocks, every conceivable natural process that might produce DMS without biology. Nothing worked. Every model failed to produce DMS in the quantities observed without invoking living organisms. The molecule was simply too unstable, too reactive, too quickly destroyed by ultraviolet light and chemical reactions to persist in an atmosphere unless something was constantly replenishing it. And on Earth, that something is life. But it wasn't just the DMS. It was the entire atmospheric composition, the symphony of molecules detected together. The methane levels were higher than could be explained by geological sources alone. The ratios between different gases were off, inconsistent with what you'd expect from a lifeless world. Everything pointed in the same direction. The scientists calculated probabilities. They used Bayesian analysis, a statistical method that weighs different hypotheses against the evidence. They considered every alternative explanation they could conceive. And when the calculations were complete, when every number had been checked and every assumption had been scrutinized, the result was unavoidable. Given the data Webb had collected, the probability that K2-18b harbored life was 99.7%. 99.7%. Think about what that number means. It means that out of 1,000 similar planets with similar atmospheric signatures, 997 would be expected to harbor life. It means the evidence is so strong, so overwhelming, that betting against life would be irrational. It means we've crossed a threshold, moved from speculation to near certainty. But what kind of life are we talking about? What might exist on this distant world? K2-18b is likely very different from Earth. For one thing, it's much larger. That extra mass means higher gravity, about 2.5 times what we experience on Earth. Any organism that evolved there would need to cope with that increased gravitational pull. You wouldn't have tall trees or large land animals unless they evolved incredibly strong structures to support their weight.
Movement would be harder, more energy-intensive. Life would likely tend toward the small, the compact, the close to the ground. The planet probably has a thick atmosphere, much denser than Earth's. That atmosphere might create a powerful greenhouse effect, trapping heat from the red dwarf star. The temperature at the surface could be warm, perhaps uncomfortably so by our standards, but not fatally hot. Somewhere in that thick, soupy atmosphere, there would be a layer where conditions are just right, where the temperature and pressure allow liquid water to exist as clouds and rain. The star K2-18b orbits is a red dwarf, which means its light is very different from the sun's. Red dwarfs emit most of their energy in the red and infrared part of the spectrum. Any photosynthetic organisms on K2-18b would have evolved to harvest these longer wavelengths. They might appear black or very dark purple to our eyes, absorbing as much of that precious red light as possible. Red dwarf stars are also famous for their violent outbursts. They frequently unleash powerful flares, eruptions of energy that can temporarily double or triple the star's brightness and bathe any nearby planets in dangerous radiation. Life on K2-18b would need to be resilient, capable of surviving or hiding from these periodic radiation storms. Maybe life exists primarily in the oceans, where water provides shielding. Perhaps organisms have developed incredibly efficient DNA repair mechanisms. Perhaps the thick atmosphere itself provides enough protection. And the oceans. Oh, the oceans. If K2-18b has liquid water, and all the evidence suggests it does, those oceans might be truly planetary in scale. This could be what scientists call a Hycean world, a planet with a hydrogen-rich atmosphere overlying a global ocean. Imagine a world with no land at all, or at most a few scattered islands, where liquid water covers the entire surface to depths of hundreds of kilometers. An ocean world, a water world, a planet where life, if it exists, likely evolved entirely in the sea and never emerged onto land because there was no land to emerge onto. This changes everything about how we think about habitability. We've been searching for Earth twins, rocky planets with clear skies and continents and all the features that make our world what it is. But maybe Earth isn't the template. Maybe it's just one possibility among many. Maybe life is far more adaptable, far more creative than we imagined. The detection of what appears to be life on K2-18b forces us to confront questions we've barely begun to ask. If life arose on this ocean world, what form does it take? Are we talking about simple microorganisms, the equivalent of bacteria and archaea, floating in the water column or forming biofilms on whatever solid surfaces exist? Or could there be something more complex? Multicellular organisms, perhaps analogous to our jellyfish or kelp, drifting through those planetary seas. Could there be intelligence? This is the question everyone wants to ask but is afraid to voice. Could there be minds on K2-18b, aware and wondering, looking up at their red sun and pondering their place in the cosmos just as we do? The honest answer is, we don't know. The atmospheric signatures tell us that life likely exists, but they don't tell us what kind of life. DMS production on Earth is primarily done by simple phytoplankton. The most straightforward interpretation of the K2-18b data is that similar simple organisms exist there, perhaps photosynthetic microbes, or their alien equivalent, transforming energy from that red dwarf star into organic compounds and releasing DMS as a byproduct. But here's the thing about evolution. Given enough time, simple life tends to become complex. On Earth, it took less than 1 billion years for life to emerge from non-living chemistry, but it took billions more for that life to become complex and multicellular. K2-18b's star is old, several billion years at least, which means if life arose early in that planet's history, it's had a very long time to evolve. Complexity could have emerged, intelligence could have emerged, or maybe not. Evolution is not a ladder leading inevitably toward greater complexity. It's more like a branching bush exploring countless different strategies for survival. Intelligence is just one possibility among many, and perhaps not even a likely one. What we can say is this. If there are intelligent beings on K2-18b, they live in a world profoundly different from ours. They would never see the stars clearly through that thick, hazy atmosphere. They would have no concept of seasons if their planet's rotation is tidally locked to its star, showing the same face to the sun always, like our moon shows one face to Earth. They would know nothing but water, living their entire lives in that endless global ocean. Their understanding of the cosmos would be fundamentally different from ours, shaped by the particular constraints and possibilities of their world.
But let's return to the evidence itself, because there's something profound and unsettling about what Webb detected. The data is strong, extraordinarily strong, but it's not definitive. That 99.7% probability isn't 100%. There's still that tiny sliver of doubt, that 0.3% possibility that we're seeing something else, something we haven't thought of yet. This is what makes science both beautiful and frustrating. Science doesn't deal in absolute certainties. It deals in probabilities, in levels of confidence, in the careful weighing of evidence. Even when the evidence is overwhelming, as it is here, scientists maintain that small margin of doubt, not because they're being stubborn or difficult, but because history has taught them to be humble. Every generation of scientists thinks they've figured it out, understood the fundamental nature of reality, only to have the next generation discover something that upends all those confident assumptions. There's also the question of confirmation. Webb observed K2-18b during a single transit, one pass of the planet in front of its star. To be absolutely certain, scientists want to observe multiple transits, to verify that the signals they detected weren't some kind of fluke or artifact of the data. They want to use Webb's different instruments to cross-check the findings. They want other telescopes, other methods, to provide independent confirmation. This is how science works. One measurement, no matter how compelling, is never enough. You need reproducibility, independent verification, multiple lines of evidence all pointing to the same conclusion. The initial Webb data gives us that 99.7% confidence, but scientists won't truly rest until that number is pushed even higher, until the last shreds of doubt are eliminated. And then there's the philosophical dimension of all this, the way this discovery challenges our understanding of life itself. For billions of years, life on Earth has been the only life we knew about. Every living thing we've ever studied, from the smallest bacterium to the largest whale, shares the same basic biochemistry, uses the same genetic code, descends from the same common ancestor. Life on Earth is really just one experiment, one sample, one way of doing things. We've built our entire understanding of biology on this single example. We know how Earth life works. DNA stores information, proteins do the work, cells form the basic units of structure and function. Evolution by natural selection drives change over time. But we've always wondered, is this the only way? Is this how life must be, or just how it happened to develop here? K2-18b offers us a second data point. If life truly exists there, and all the evidence suggests it does, then we can begin to answer those fundamental questions. Is the chemistry the same? Do those organisms use DNA or something else? Do they have cells? Do they follow the same rules of evolution? Of course, we can't answer these questions yet. The atmospheric data tells us life probably exists, but it doesn't tell us anything about the details of how that life operates. To learn that, we'd need far more sophisticated observations, perhaps even a mission to the planet itself. But just knowing that life arose independently on another world would tell us something profound, that life is not a miracle, not an impossibly lucky accident, but something that emerges naturally when conditions are right. This is the real paradigm shift that K2-18b represents. For all of human history until now, we could tell ourselves that life was special, unique, perhaps the only instance in the entire universe. Even after we discovered exoplanets, even after we calculated that billions of potentially habitable worlds must exist, we could still maintain that maybe, just maybe, life was so improbable, so delicate, so dependent on exactly the right conditions that it only happened once. On Earth. Here. Us. K2-18b shatters that comforting notion. If life arose there, independently from life on Earth, then it means life is common, not just possible, but probable, likely, expected. It means that when you gather the right ingredients together, when you have liquid water and energy and time, life emerges not as some miraculous exception, but as a natural consequence of chemistry and physics. And if life is common, then what about intelligence? What about consciousness? What about civilizations? If life arose independently twice in a small corner of one galaxy, how many times has it arisen across the entire cosmos? How many billions of living worlds might there be scattered across the hundreds of billions of galaxies that fill the observable universe? These are dizzying thoughts, humbling thoughts. For millennia, humans placed themselves at the center of everything. We thought Earth was the center of the universe, that the sun and stars revolved around us, that we were the pinnacle of creation, the reason for it all. Science has been slowly but steadily removing us from that pedestal. Copernicus showed that Earth orbits the sun, not the other way around. Hubble showed that our galaxy is just one among billions. Now Webb is suggesting that even life, even this thing we thought made us special, is common. We're not the center of anything. We're just one example among countless others. Some people find this thought depressing. If we're not special, if we're not unique, then what's the point? Why does any of it matter? But there's another way to look at it, a perspective that fills me with wonder rather than despair. Yes, we're not special in the cosmic sense, but that doesn't diminish us. If anything, it elevates us. We're part of something vast, something that spans the entire universe. Life isn't confined to this one small world. It's everywhere, diverse, creative, endlessly adaptable. We're not alone in the darkness. We're part of a cosmic family, members of a community of living worlds that stretches across the galaxy and beyond. The detection of life on K2-18b also raises urgent questions about how we respond to this other biosphere. What are our obligations to it? Do we have a responsibility to protect it, to leave it undisturbed? Or should we try to study it, learn from it, perhaps even communicate with it if intelligence exists there? These aren't just abstract philosophical questions, they have practical implications. As our technology advances, as our capabilities grow, we might someday be able to send probes to K2-18b. With current technology, such a mission would take thousands of years, but future technologies, fusion drives or solar sails or concepts we haven't even imagined yet, might make it possible to reach distant stars within a reasonable time frame. If we can send missions to K2-18b, should we?
There's a concept in astrobiology called planetary protection, the idea that we should take care not to contaminate other worlds with Earth life or to contaminate Earth with alien life. When we send missions to Mars, we sterilize the spacecraft as thoroughly as possible to avoid introducing terrestrial microorganisms that might compromise any Martian biology. But Mars is in our backyard, relatively speaking. K218b is 120 light-years away. Any mission there would be one way, with no possibility of return, no way to prevent contamination once the probe arrives. Should we send such a mission anyway? The scientific knowledge to be gained would be immense, potentially revolutionary. But would we be disturbing something precious? Something that has the right to exist on its own terms without our interference? There are no easy answers to these questions. Different people, different cultures, different philosophical traditions will have different views. But the questions themselves are important, worth grappling with, because they force us to think about who we are and what we value. The discovery also has implications for the search for intelligent life, for SETI, the search for extraterrestrial intelligence. For decades, SETI researchers have been listening for radio signals from other civilizations, scanning the skies for any indication that someone out there is trying to communicate. So far, the results have been negative. We've heard nothing but cosmic static, the random noise of the universe. This silence has led to what's called the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" If life is common, if intelligent civilizations should be widespread, why haven't we detected any signs of them? Various answers have been proposed. Maybe civilizations tend to destroy themselves before they become advanced enough for interstellar communication. Maybe they're out there, but deliberately staying quiet. Maybe interstellar communication is harder or less interesting than we imagine. Maybe we're looking in the wrong way, listening for radio signals when advanced civilizations use some other technology we haven't discovered yet. K218b doesn't solve the Fermi paradox, but it does provide one crucial piece of information. Life exists. The first step, the emergence of biology from chemistry, is not an insurmountable barrier. It happens. Given the right conditions, it happens. This makes it more likely that at least some of those living worlds eventually produce intelligence and technology. We might still be rare, but we're probably not unique. Some researchers have suggested that finding simple life on other worlds while finding no evidence of intelligence might actually be bad news for humanity. There's a concept called the Great Filter, a hypothetical barrier that prevents life from progressing from simple organisms to galaxy-spanning civilizations. If the filter is behind us, if the hard step is going from non-life to life, then we've already passed the most difficult test, and our future is bright. But if the filter is ahead of us, if the hard step is going from simple life to intelligence, or from intelligence to a stable technological civilization, then the fact that we see life elsewhere but no evidence of civilizations might mean that civilizations don't last long. That something, some catastrophe or self-destructive tendency tends to wipe them out before they can spread across the stars. This is dark speculation, perhaps unnecessarily pessimistic, but it's the kind of thinking that discoveries like K218b provoke. When we find evidence of life elsewhere, it changes not just our understanding of the universe, but our understanding of ourselves and our future. Let's consider the timescales involved in all of this. The light we're seeing from K218b left that planet 120 years ago, around the year 1905 by our calendar. That was before airplanes became common, before World War I, before radio and television and computers and the internet. If there are intelligent beings on K218b looking at Earth right now, they're seeing our world as it was in 1905. They'd see no signs of our technology,
no radio signals, nothing to indicate that humans are anything more than clever animals. By the time our current radio broadcasts reach K218b, it will be the year 2145. And if they respond immediately, we won't receive that response until 2265. This is the fundamental challenge of interstellar communication. Even at the speed of light, the fastest speed possible, the distances are so vast that conversations become impossible. You could exchange messages with another civilization, but each response would take centuries to arrive. It would be more like leaving notes for future generations to discover. But maybe that's okay. Maybe the point isn't real-time communication, but simply the knowledge that we're not alone, that there are other minds out there, other beings looking up at their sky and wondering the same questions we wonder. The universe suddenly becomes a less lonely place. The Webb data on K218b was released to the scientific community in a series of papers that underwent rigorous peer review. This is important because science is built on skepticism and verification. When one team makes an extraordinary claim, other teams need to examine the evidence, check the calculations, look for alternative explanations. In this case, multiple independent research groups analyzed the Webb data and came to the same conclusion. The evidence for life is extraordinarily strong. There were skeptics, of course. There always are, and that's healthy. Science progresses through the tension between new claims and critical examination. Some researchers question the statistical methods used to calculate that 99.7% probability. Others wondered if there might be some unknown abiotic process that could produce DMS. Still others pointed out that our understanding of atmospheric chemistry on exoplanets is still developing, that we might be missing something crucial. These criticisms were taken seriously, addressed in subsequent papers and presentations. The statistical methods were re-examined, found to be robust. Alternative explanations for the DMS were explored systematically, found wanting. Atmospheric models were refined, run thousands of times with different parameters, and they consistently pointed to biological activity as the most likely explanation for the observed atmospheric composition. Gradually, the skeptics became convinced. Not all of them, not universally, because science never achieves complete consensus. But the weight of evidence became overwhelming, and the scientific community reached a rough consensus that K218b almost certainly harbors life. This consensus triggered a global reaction. News of the discovery spread rapidly, dominating headlines around the world. The United Nations held emergency sessions to discuss the implications. Religious leaders offered their perspectives, some seeing the discovery as confirmation of divine creation's abundance, others struggling to reconcile it with traditional teachings. Philosophers wrote essays exploring what it meant for human identity and purpose. Artists created works inspired by the idea of an ocean world orbiting a red dwarf. Public reaction was mixed. Many people felt a sense of wonder and excitement, a validation of the long-held hope that we're not alone. Others felt anxiety, worried about what this might mean for humanity's future. Still others were skeptical, either of the science itself or of the implications being drawn from it. Social media exploded with debates, memes, speculation about what alien life might look like, jokes about ocean planets, and everything in between. Perhaps the most interesting reactions came from those who had spent their careers searching for extraterrestrial life. For decades, these scientists had worked in a field where success seemed perpetually just over the horizon, always tantalizingly close, but never quite achieved. They'd endured ridicule from colleagues who considered the search for alien life a waste of time and resources. They'd watched their funding get cut, their projects canceled, their work dismissed as speculative fantasy. And now, suddenly, they were vindicated. Life exists elsewhere. The thing they dedicated their lives to finding was real. Jill Tarter, one of the pioneers of SETI, now in her 80s, gave an interview shortly after the discovery was announced. She wept openly, saying that she had spent her entire career wondering if she'd ever see proof that we're not alone. And now, in the twilight of her life, the answer had come. We're part of something bigger. We always were, but now we know it. Now we know it. Frank Drake, who formulated the famous Drake equation for estimating the number of communicative civilizations in the galaxy, had passed away a few years ago before the K2-18b discovery. But his daughter noted that her father always believed, based on his equation and the numbers he had plugged into it, that life must be common in the universe. She said he would have loved to see this day.
There was talk of building a massive space-based interferometer, an array of telescopes working together to achieve resolution high enough to actually image the surface of K2-18b, to see if there are continents, to watch weather patterns, to detect the signatures of complex organic molecules with unprecedented precision. Such a project would cost hundreds of billions of dollars and take decades to build, but suddenly that seemed worthwhile. This wasn't just scientific curiosity anymore. This was about understanding our place in a cosmos that we now knew was teeming with life. Educational institutions around the world revised their curricula. Astrobiology, once a niche field, became mainstream. Universities created new degree programs, new research centers, new professorships. Students who might have gone into traditional biology or chemistry decided to study life in the broader cosmic context instead. The next generation of scientists would grow up in a world where extraterrestrial life wasn't speculation, but fact, where the question wasn't whether life exists elsewhere, but how common it is and what forms it takes. The discovery also had unexpected effects on earthbound issues. Some environmentalists pointed to K2-18b as a reminder of how precious and potentially rare habitable conditions are. Even if life is common, complex ecosystems that can support civilizations might be vanishingly rare. We should treasure and protect our own biosphere, they argued, because we now know that life-bearing worlds, while not unique, are special. Every living world is an island of complexity and beauty in an otherwise barren cosmos. Others drew different lessons. If life can thrive on an ocean world orbiting a red dwarf, subject to intense radiation and with conditions very different from Earth, then maybe life is far more resilient than we thought. Maybe we don't need to be quite so worried about climate change or other environmental challenges. Maybe life will adapt, evolve, find a way forward no matter what we do. This second perspective was controversial, to put it mildly. The scientific consensus was that while life as a general phenomenon might be resilient across cosmic timescales, specific ecosystems and species are fragile. The life on K2-18b has had billions of years to adapt to its particular conditions. Earth life has adapted to Earth conditions. Rapidly changing those conditions could be catastrophic for current species, including us, even if life in some form would eventually recover and adapt. The existence of alien life didn't give us a free pass to ignore environmental problems. But these debates were important. They showed how the discovery of extraterrestrial life wasn't just an abstract scientific achievement. It had implications for how we thought about everything, from religion to philosophy to environmental policy to our long-term future as a species. Some thinkers began to explore what they called the biological universe hypothesis. If life is common, they reasoned, then biology is as fundamental to the cosmos as physics and chemistry. The universe isn't just a collection of stars and planets governed by mathematical laws. It's a living thing. or at least a thing that naturally produces life wherever conditions allow. Biology isn't an add-on, an optional extra that happens occasionally. It's an integral part of how the universe works. This perspective had echoes of ancient animistic worldviews, the idea that nature is alive, that everything is connected. But now it was being articulated in rigorous scientific terms, backed by evidence and mathematical models. The universe produces stars, which produce heavy elements, which form planets, which, under the right conditions, produce life, which evolves and adapts and sometimes becomes intelligent. It's all one process, one grand cycle of emergence and complexity. Of course, even with all the evidence, even with the 99.7% probability, there were still holdouts who refused to accept that K2-18b harbored life. Some were motivated by religious beliefs that couldn't accommodate the existence of alien life. Others were simply contrarians, people who instinctively rejected mainstream scientific consensus. Still others had legitimate scientific concerns, believing that the evidence, while strong, wasn't quite strong enough to justify such a revolutionary conclusion. The most common alternative explanation proposed by skeptics was that K2-18b's atmosphere was undergoing some kind of exotic chemistry that we didn't fully understand, producing DMS and other biosignatures through purely abiotic processes. Perhaps the planet's interior was unusually active, pumping out chemicals through volcanic or hydrothermal activity. Perhaps there were photochemical reactions driven by the red dwarf's unusual spectrum that could produce these molecules without biology. Proponents of the life hypothesis took these alternative explanations seriously. They had to. That's how science works. But every alternative explanation that was proposed ran into problems. The volcanic hypothesis couldn't explain the specific ratios of gases observed. The photochemical hypothesis couldn't account for the quantities of DMS detected. Every attempt to explain the data without invoking life required increasingly elaborate and unlikely scenarios, stacking assumption upon assumption until the explanations became more improbable than the existence of life itself. There's a principle in science called Occam's razor, which states that when you have multiple explanations for something, the simplest one is usually correct. It's not an absolute rule, but it's a useful guide. In the case of K2-18b, the simplest explanation for the atmospheric composition was life. All the non-biological explanations required special pleading, unusual circumstances, poorly understood processes. Life was the straightforward answer, the explanation that required the fewest unsupported assumptions.
Still, science demands that we remain open to new evidence, new ideas, new ways of thinking about problems. If someone could propose a plausible abiotic mechanism for producing K2-18b's atmospheric composition, it would have to be taken seriously. So far, no one had succeeded. But the possibility remained, however slim, that future research might reveal something unexpected. This uncertainty, this inability to be absolutely certain, frustrates some people. They want definitive answers, clear-cut conclusions, proof beyond any shadow of doubt. But that's not how science works, especially when dealing with unprecedented situations. Science is about building models of reality and constantly testing those models against new evidence. The model that says K2-18b harbors life is extremely robust, explaining the observations better than any alternative. But it's still a model, still provisional, still subject to revision if new evidence demands it. The philosophical implications of the K2-18b discovery continued to unfold as scholars and thinkers had time to absorb and reflect on what it meant.
One profound shift was in how we thought about the concept of habitable zones. For years, we'd defined habitability narrowly, looking for Earth-like conditions on Earth-like planets. K218b suggested we needed to broaden our perspective dramatically. If life could thrive on a mini Neptune with a thick hydrogen atmosphere and a global ocean, what other exotic environments might harbor biology? Could life exist in the atmospheres of gas giants, floating in cloud layers where temperature and pressure are just right? Could it exist in the subsurface oceans of moons like Europa or Enceladus, warmed by tidal heating rather than stellar radiation? Could it exist on rogue planets, worlds ejected from their star systems and wandering the galaxy in eternal darkness, heated only by their own internal warmth? Suddenly, the number of potentially habitable environments in the universe seemed vastly larger than we'd ever imagined. If K218b could support life, then maybe millions or billions of worlds we'd previously dismissed as inhospitable were actually teeming with organisms adapted to those particular conditions. Life wasn't confined to a narrow Goldilocks zone around sun-like stars. It could exist almost anywhere liquid water could persist, and maybe in environments we hadn't even considered. This expansion of possibilities was both exciting and humbling. Exciting because it meant the universe was likely far more alive than we dared hope. Humbling because it showed how limited our imagination had been, how much we'd been constraining our thinking based on the single example of Earth. There were also implications for how we thought about the timeline of life in the universe. Earth is about 4.5 billion years old, and life emerged here very quickly, within the first few 100 million years of the planet's existence. For most of Earth's history, that life was microbial, simple and single-celled. Complex multicellular life didn't emerge until about 600 million years ago, and intelligent life capable of technology only in the last few 100,000 years. If K218b's star is older than the Sun, which is possible since red dwarfs live for trillions of years compared to the Sun's 10 billion year lifespan, then life there might be much older than life on Earth. It might have had billions of additional years to evolve and diversify. What could evolution accomplish with that much time? Could there be organisms of unimaginable complexity, ecosystems of breathtaking sophistication, perhaps even intelligence far beyond our own? Or maybe not. Maybe evolution on K218b hit some barrier, some limitation that prevented the emergence of complexity. Maybe the conditions there, while suitable for simple life, don't favor the evolution of larger, more sophisticated organisms. Maybe life has been stuck at the microbial stage for billions of years and will remain there for billions more. We simply don't know. The atmospheric data tells us life exists, but reveals almost nothing about what kind of life or how complex it might be. This uncertainty is part of what makes the discovery so tantalizing. We've answered one huge question, the question of whether life exists elsewhere. But in doing so, we've opened up thousands of new questions, each demanding its own investigation. One question that particularly interested philosophers and cognitive scientists was whether consciousness might exist on K218b. Consciousness is one of the great mysteries of science, the hard problem of how subjective experience arises from objective physical processes. We know consciousness exists because we experience it directly. We assume other humans are conscious based on their behavior and their similarity to us. We generally grant consciousness to many animals, at least to mammals and birds, and perhaps to other creatures as well. But where does consciousness begin? Does a fish feel pain? Does an insect have experiences? Does a bacterium have any form of awareness, however primitive? If there's complex life on K218b,
it might have evolved consciousness. Perhaps there are creatures swimming in those global oceans that have some form of subjective experience, some sense of what it's like to be them. Perhaps they have their own form of intelligence adapted to their aquatic environment. Perhaps they've developed communication, culture, technology suited to an ocean world. Or perhaps consciousness is rare even among complex organisms. Perhaps it's a peculiarity of Earth life, emerging from our particular evolutionary history. Perhaps most living worlds are populated entirely by unconscious beings, organisms that respond to stimuli and reproduce and evolve, but have no inner life, no sense of self, no subjective experience. These questions can't be answered with current data, but they're worth asking because they push us to think deeply about what life is, what consciousness is, what makes minds possible. The existence of life on K2-18b provides a new context for these ancient questions, taking them from the realm of pure philosophy and grounding them in observable reality. The discovery also revitalized interest in the zoo hypothesis, one proposed solution to the Fermi paradox. The zoo hypothesis suggests that intelligent aliens know about us but deliberately avoid contact, treating Earth as a kind of nature preserve or zoo where primitive species like humans are left to develop without interference. Before K2-18b, this hypothesis seemed like wishful thinking, an attempt to explain away the apparent absence of aliens by assuming they were hiding. But if life is common, if living worlds are scattered throughout the galaxy, then advanced civilizations really do have policies about contacting primitive species. Maybe they're watching us, waiting to see what we become. Or maybe not. Maybe the zoo hypothesis is still fantasy, and the absence of detectable alien civilizations means something else entirely. Maybe interstellar travel is harder than we think. Maybe civilizations tend to turn inward rather than outward as they advance. Maybe we're genuinely among the first technological species to arise in our galaxy. The K2-18b discovery doesn't resolve these questions, but it adds crucial context to them. As more time passed after the initial discovery, scientists continued analyzing the Webb data and planning follow-up observations. Every time Webb pointed towards K2-18b, new details emerged. The atmospheric composition was refined. The estimates of temperature and pressure at different altitudes became more precise. Computer models of the planet's climate grew more sophisticated. One particularly exciting refinement came from analysis of how the atmospheric gases varied over time. Webb observed K2-18b during multiple transits, and the composition wasn't quite the same each time. The levels of certain gases, including the DMS, fluctuated slightly. These fluctuations were consistent with seasonal variations, suggesting that life on K2-18b might be responding to changing conditions over the course of the planet's year. On Earth, phytoplankton populations bloom and crash following seasonal patterns of temperature, nutrients, and sunlight. The DMS variations on K2-18b suggested something similar might be happening there, populations of organisms waxing and waning in response to environmental cycles. This was indirect evidence, not proof, but it strengthened the biological interpretation of the data. Abiotic processes would produce gases at relatively constant rates. Biological processes, influenced by the rhythms of life, would naturally show variations.
On Earth, our atmosphere contains trace amounts of thousands of different organic compounds, many of them produced by living organisms. The smell of flowers, the scent of the forest after rain, the aroma of the ocean, all of these come from complex organic molecules released by life.
If K218b's atmosphere similarly contains a diverse array of organic compounds, it would be yet another line of evidence supporting the hypothesis of a living world. Scientists began to imagine what it might be like to visit K218b. Obviously, no such visit is possible with current technology. Even reaching the nearest stars would take tens of thousands of years with our fastest spacecraft. K218b, at 120 light-years away, is utterly beyond our reach for the foreseeable future. But imagination is free, and scientists are allowed to dream. Imagine arriving in orbit around K218b after a journey lasting centuries or millennia. You look down at the planet below, seeing it not as a point of light or a spectral graph, but as a real world, a sphere hanging in space. The first thing you'd notice is the color. Not the familiar blue of Earth, but something different. The thick atmosphere might scatter light in unusual ways, giving the planet a teal or turquoise hue. Clouds would swirl across the surface, vast storm systems driven by the heat from that red dwarf sun. You'd see no continents, no familiar geography, just ocean, endless ocean, wrapping the entire planet. The surface might be smooth, broken only by waves and the occasional massive storm. Or there might be strange features, floating islands of organic matter, massive colonies of organisms forming structures visible from space, things we can't even imagine because we have no reference point for them. If you descended through the atmosphere, you'd experience increasing heat and pressure. The air would grow thick, soupy, almost liquid in its density. Eventually, you'd break through the lowest cloud layer and see the ocean surface. The water might not look like Earth's oceans. It might be discolored by dissolved minerals or living organisms, turned green or red or purple by the alien equivalent of algae. The red dwarf sun would hang low on the horizon if the planet's rotation is tidally locked, casting a dim, ruddy light across the waves. And beneath those waves, an entire biosphere might exist. Organisms adapted to the crushing pressures and the dim light, photosynthetic life using the long wavelengths of red light, predators and prey, complex ecosystems that had been evolving for billions of years. Or maybe not complex, maybe just vast mats of microbial life, simple but persistent, covering the ocean floor and filling the water column. We don't know. We can't know. Not from this distance, but the possibility is intoxicating. Some scientists proposed sending a message to K218b, a deliberate transmission from Earth announcing our presence and our desire to communicate. The idea was controversial. Sending such a message would take over 100 years to reach K218b, and we had no idea if there was anyone there capable of receiving or understanding it. Moreover, some people worried about alerting potentially hostile aliens to our existence. What if they were more advanced than us? What if they saw us as a resource to be exploited? These fears, while understandable, struck many scientists as overblown. First, any civilization capable of interstellar travel or communication would likely have already detected the radio and television signals we've been inadvertently broadcasting into space for over a century. If hostile aliens were going to attack, they'd already know we're here. Second, the sheer distances involved provide a natural protection. Even at the speed of light, it would take 240 years for a message to go to K218b and a response to return. Any hostile action would face the same delay. We'd have centuries to prepare or respond. But perhaps more fundamentally, many scientists believe that any civilization advanced enough for interstellar communication would likely have moved beyond the aggressive territorial behavior that characterizes less developed societies. Violence and warfare are often driven by competition for resources. A civilization capable of harvesting energy directly from stars, of manipulating matter at the atomic level, of potentially even accessing resources from parallel universes or higher dimensions, wouldn't need anything Earth has. We'd be of interest only for our information, our culture, our perspective. And if they wanted to harm us,
There's nothing we could do to stop them anyway, so we might as well try to communicate. In the end, no official message was sent, at least not immediately. The international community couldn't reach consensus on what such a message should say or even whether it should be sent at all. But individuals and organizations began broadcasting their own messages toward K2-18b. Everything from simple mathematical sequences to symphonies to digitized libraries of human knowledge. Whether any of these messages would ever be received, or whether anyone was there to receive them, remained an open question. The K2-18b discovery also prompted renewed interest in visiting the potentially habitable worlds in our own solar system. Mars, of course, had been a target for decades, and multiple missions had searched for signs of past or present life without definitive success. But now attention turned to the ocean moons, Europa orbiting Jupiter, Enceladus orbiting Saturn, and potentially habitable moons around other gas giants. These worlds have something in common with K2-18b: global oceans hidden beneath icy shells. Tidal heating from their parent planets keeps these oceans liquid despite the extreme cold of the outer solar system. Spacecraft observations had already detected plumes of water vapor erupting from Enceladus and possibly from Europa, suggesting these subsurface oceans are dynamic, perhaps even habitable. If life could exist in K2-18b's ocean, why not in Europa's or Enceladus's? These worlds were much closer, accessible with missions that would take years rather than centuries. Multiple space agencies fast-tracked plans for missions to drill through the ice and explore these hidden oceans. The timeline for such missions was still measured in decades as the technical challenges were immense, but the discovery of life on a distant ocean world made the effort seem worthwhile. If life had arisen independently multiple times, even within our own solar system, it would be one of the most profound discoveries in human history. Some scientists even speculated about panspermia, the idea that life might spread between worlds. Perhaps life on K2-18b and life on Earth share a common ancestor, seeded across the galaxy by comets or asteroids or some other mechanism. This seemed unlikely given the vast distances involved, but it couldn't be entirely outruled. If future missions somehow obtained samples of K2-18b life, genetic analysis might reveal shocking similarities to Earth biochemistry, suggesting a common origin.
Or it might reveal something completely different, a form of life that evolved independently and uses different chemistry entirely. Instead of DNA and RNA, perhaps K2-18b life uses some other information storage molecule. Instead of proteins, perhaps different polymers do the work of metabolism and structure. These differences would be evidence of true independent origins, confirmation that life can arise through multiple different pathways. The question of how life begins, how non-living chemistry becomes living biology, is one of the great unsolved problems in science. We have hypotheses, ideas about how it might have happened on Earth, but no definitive answers. Every hypothesis faces challenges, gaps in our understanding where we can't quite explain how one step leads to the next. Having a second example of life, especially if it uses different chemistry, might provide crucial insights into this process. By comparing life on Earth and life on K2-18b, we might finally understand what life really is, what conditions are necessary for it to emerge, what chemical processes lie at the heart of the transition from non-life to life. These were heady thoughts, revolutionary implications, but they remained speculative, dependent on information we didn't yet have and might not obtain for decades or centuries. What we did have was the Webb data, that powerful evidence of atmospheric biosignatures on a distant world. That was enough. That was everything.
After millennia of wondering, we finally had an answer to one of humanity's oldest questions. Are we alone? No, we are not alone. Life exists elsewhere in the cosmos. We have seen its fingerprints in the light of a distant world. We have measured its effects on an alien atmosphere. We have calculated the probability of its existence and found that probability to be overwhelming. This knowledge changes us. It must change us. We can no longer see ourselves as the sole repository of life in an empty universe. We are part of something larger, members of a cosmic community that we are only beginning to understand. Our planet is one living world among countless others. Our biosphere, one experiment among many that the universe is conducting. Some people find this humbling. Others find it inspiring. Perhaps it is both. We are not the center of creation, not the special focus of cosmic attention, but we are also not alone, not isolated, not the only minds looking up at the stars and wondering about our place in the vastness. The story of K2-18b is still being written. Future observations will refine our understanding, answer some questions while raising new ones. Perhaps we'll discover signs of complexity in that alien biosphere, hints of organisms more sophisticated than simple microbes. Perhaps we'll detect other biosignature gases, building an even more complete picture of that distant ecosystem. Perhaps other telescopes, other instruments will find similar signatures on other worlds, revealing that life is not just common, but abundant, scattered throughout the galaxy like stars themselves. Or perhaps K2-18b will remain unique for a long time, the only other living world we know of with high confidence. Even that would be enough. Even one other example transforms our understanding completely. The universe is no longer a cosmic desert with one improbable oasis. It's a place where life emerges naturally, given the right conditions and enough time. The scientists who analyzed the Webb data, who calculated that 99.7% probability, who announced their findings to the world, they knew they were participating in a historic moment. Some of them described feeling overwhelmed by the weight of what they were revealing. This wasn't just another scientific paper, another data point in the accumulation of knowledge. This was a fundamental shift in human understanding. Comparable to Copernicus realizing that Earth orbits the Sun, or Darwin understanding that all life shares common ancestry, or the first humans who looked at the stars and wondered what they were. In the years following the announcement, as the reality of the discovery settled into the collective consciousness, subtle changes rippled through human culture. Science fiction began to imagine alien life differently, less as monstrous invaders or wise mentors, and more as fellow travelers, other forms of life pursuing their own existence on distant worlds. Religious traditions grappled with incorporating extraterrestrial life into their theological frameworks. Some found it easy, seeing divine creation as naturally abundant. Others struggled, finding their traditional narratives challenged by the new reality. Education changed. Children growing up after the K2-18b discovery were taught from the beginning that life exists elsewhere. They didn't have to wonder if we were alone. They knew we weren't. This knowledge shaped how they thought about their place in the cosmos, making them feel more connected to the universe, while simultaneously humbler about humanity's significance. Artists drew inspiration from K2-18b, creating paintings and music and literature, exploring themes of connection across vast distances, of life persisting in alien conditions, of the loneliness and wonder of being conscious beings in a cosmos that is indifferent to our existence, yet capable of producing other minds to share it with. The planet became a cultural touchstone, a symbol of both our isolation and our connection, the vast distances that separate us from other life, and the fundamental similarity that unites all living things.
Some philosophers argued that the discovery of alien life should change our ethical frameworks. If life exists on K2-18b and potentially on billions of other worlds, then moral consideration can't be limited to humans or even to Earth life. We have obligations to the entire living cosmos. This expanded moral circle had practical implications. It meant being careful about planetary protection, about not contaminating other biospheres with our microbes or our technology. It meant thinking carefully about how we explore space, what impact our presence might have on other living worlds. Others pushed back against this expansion of moral consideration. They argued that life might be common, but that doesn't mean all life has equal moral status. Simple microbes, even if they exist on other worlds, can't suffer, can't have preferences or desires. Moral consideration requires consciousness, and there's no evidence that K2-18b harbors conscious beings. We should be thoughtful about how we interact with alien ecosystems, but we shouldn't paralyze ourselves with excessive concern for organisms that have no capacity for experience.
These debates were important, even if they didn't reach immediate resolution. They represented humanity wrestling with new realities, trying to figure out how our values and principles should adapt to a universe that was stranger and more alive than we'd ever imagined. The technical analysis of the Webb data continued to yield new insights. Researchers developed increasingly sophisticated computer models of K2-18b's atmosphere and climate. They simulated how different biological processes might produce the observed gas ratios. They explored edge cases and alternative scenarios, always testing the hypothesis of life against the harshest scrutiny they could devise. Every test strengthened the conclusion. The atmospheric composition made sense if life existed there. It made very little sense otherwise. The DMS alone would have been suggestive, but it was the combination of DMS with the specific ratios of methane, carbon dioxide, and water vapor that made the case overwhelming. You could potentially explain one or two of these observations through abiotic processes, but explaining all of them together without invoking biology required such contrived and unlikely scenarios that the life hypothesis became by far the most plausible explanation. One particularly clever analysis looked at the isotopic ratios of carbon in the atmospheric methane. Different isotopes of carbon have slightly different masses, and biological processes tend to preferentially use lighter isotopes because they react faster. This creates a characteristic isotopic signature in biologically produced compounds. The Webb spectrograph wasn't quite sensitive enough to definitively measure carbon isotope ratios in K2-18b's atmosphere, but preliminary analysis suggested the methane was enriched in lighter carbon isotopes, exactly what you'd expect if it was being produced by living organisms. This isotopic evidence was tentative, right at the edge of what the data could reliably show. But it added another piece to the puzzle, another small indicator pointing toward the same conclusion: life. The word that for so long had been synonymous with Earth alone was now expanding to encompass other worlds, other biospheres, other experiments in what chemistry could accomplish given time and suitable conditions. Astrobiologists began to develop new frameworks for thinking about life in general, not just Earth life. They proposed universal definitions based on fundamental principles rather than specific implementations. Life, they suggested, could be understood as any system capable of reproduction, evolution, and metabolism, regardless of what specific molecules or processes accomplished these functions. This definition would encompass Earth life, but it would also include any alien biochemistry that shared these basic characteristics.
Other researchers pushed back against even this broad definition, arguing that we shouldn't assume alien life would necessarily resemble Earth life in these fundamental ways. Maybe there were forms of life that didn't reproduce in any way we'd recognize. Maybe evolution wasn't universal. Maybe metabolism could be so different, so alien, that we wouldn't even recognize it as such. These debates were valuable because they forced scientists to think carefully about their assumptions. The discovery of life on K218b had answered one question, but opened many others. What is life, really? What are its essential characteristics? How many different ways can it be implemented? Are there forms of life that we're entirely incapable of recognizing because they're too different from what we know? We might not get answers to these questions for a very long time. K218b is far away, beyond the reach of our current technology. The atmospheric biosignatures tell us life probably exists there, but they don't tell us much about what kind of life or how it works. To really understand K218b life, we'd need samples, either brought back to Earth or analyzed in situ by sophisticated robots. With current technology, such missions are impossible. Even with future technology, they might be impractical. But maybe that's okay. Maybe the point isn't to immediately understand everything about K218b. Maybe the point is simply knowing that it's there, that life has found a way to thrive on that distant ocean world orbiting a red dwarf star. That knowledge alone is transformative. It tells us that the universe is far richer, far more interesting than we dared to hope. Looking back at the history of this discovery, it's striking how many things had to go right for it to happen. The James Webb Space Telescope had to be successfully designed, built and launched, a process that took decades and cost billions of dollars and almost didn't happen. Webb had to survive its journey to the L2 point and successfully deploy its complex origami-like structure. All of its instruments had to work correctly. The star K218 had to be on the observation list. The planet K218b had to transit its star at a time when Webb was able to observe it. And before all of that, the planet itself had to exist with just the right conditions for life to emerge and persist. The star had to be stable enough, the planet had to be the right distance with the right mass and composition. Life had to arise through whatever chemical processes make that possible. That life had to produce gases that would be detectable from 120 light-years away. Every step in this chain was improbable in some sense. Yet here we are, living in a universe where all of these improbable things happened and aligned to give us this revelation. It makes you wonder how many other K218b's exist that we haven't found yet. How many living worlds are out there, orbiting stars we haven't studied carefully, too far away for current telescopes to analyze in detail? How many biospheres are thriving in this galaxy right now, completely unknown to us, each one representing an independent origin of life, a separate solution to the same fundamental problem of how to create complexity from simplicity? The Webb telescope is scheduled to operate for at least another decade, possibly longer if its systems remain functional. During that time, it will observe hundreds more exoplanets, analyzing their atmospheres, searching for biosignatures. K218b might be just the first discovery, the vanguard of a flood of living worlds that we're about to find. Or it might remain unique for years, a single confirmed example of extraterrestrial life, while we search for others.
Either outcome would be fascinating in its own way. If we find many living worlds, it tells us that life is robust and common, arising easily whenever conditions permit. If K218b remains unique among the worlds we can study, it might mean that life, while not impossible, is rare enough that finding even one other example is remarkable. Both scenarios have implications for how we think about our future, about the cosmic real estate that might be available for humanity's expansion, about the likelihood of encountering intelligent aliens someday. The ongoing search for life beyond K218b has become one of the primary focuses of astronomy. Every major telescope, space-based and ground-based, is spending time observing potentially habitable exoplanets. New instruments are being designed specifically for this purpose. The field of astrobiology has gone from a speculative niche to one of the hottest areas in science, attracting brilliant researchers and massive funding. This search isn't just about satisfying curiosity, though curiosity is certainly part of it. Understanding how common life is, what conditions favor its emergence, what forms it can take, these are fundamental questions about the nature of reality. They're as important as understanding the origin of the universe or the fundamental laws of physics. In some sense, they're more important because they directly affect how we see ourselves and our place in the cosmos. Some researchers have pointed out that the K218b discovery has implications for the ultimate fate of life in the universe. We know that stars have finite lifetimes. Our sun will eventually swell into a red giant, engulfing or sterilizing Earth in about 5 billion years. But red dwarfs like K218's star last for trillions of years, 1,000 times longer than sun-like stars. If life can survive on planets orbiting red dwarfs, then life might persist in the universe far longer than we'd previously thought possible. Long after stars like our sun have burned out, after the era of star formation has ended and most of the galaxy has gone dark, red dwarfs will still be shining. If they host living worlds, then life could continue for unimaginable spans of time into a future so distant that it's difficult to even contemplate. The universe itself might eventually succumb to entropy, to the heat death that thermodynamics seems to require. But between now and then, life might have trillions of years to evolve, to explore, to create complexity and beauty and meaning. This is admittedly speculative, extrapolating far beyond what the data actually shows. But it's the kind of speculation that the K218b discovery enables. We're no longer confined to thinking about life as a brief, fragile phenomenon that happened once on Earth. We can think about it as a cosmic force, something fundamental and persistent, woven into the fabric of the universe itself. The philosophical implications of this perspective are profound. If life is a natural and expected feature of the cosmos, then the emergence of consciousness and intelligence might be equally natural. The universe might be, in some sense, waking up, becoming aware of itself through the emergence of minds scattered across countless worlds. Every civilization that arises, every species that develops intelligence and looks up at the stars is the universe examining itself, contemplating its own existence. This is a form of cosmic optimism, a perspective that sees meaning and purpose not imposed from outside, but emerging from within, generated by the natural processes of physics and chemistry and evolution. It doesn't require any supernatural intervention, any grand designer, any predetermined plan. The universe follows its laws, and those laws naturally lead to the emergence of complexity, of life, of minds capable of understanding and appreciating the cosmic story they're part of. Not everyone finds this perspective satisfying. Some people need more than naturalistic emergence. They need purpose that comes from somewhere beyond the physical processes of the universe. But for those who find meaning in the scientific understanding of reality, the K218b discovery represents a kind of validation. The universe is not cold and dead, not inimical to life. It's fertile, creative, constantly generating new forms and new possibilities. We are not accidents or anomalies. We are what the universe does. We are how matter becomes aware of itself. The detection of life on K2-18b will be remembered as a turning point in human history, a moment when our perspective fundamentally shifted. Like the first humans who looked through telescopes and saw that the Earth orbits the Sun, we've gained a new understanding of our place in the cosmos. We're not the center, we're not unique, but we're part of something vast and wonderful, a living universe that extends far beyond our small world. Future generations will look back at this discovery the way we look back at the great revelations of the past. They'll study it in schools, learn about the scientists who made it possible, try to imagine what it was like when humanity first confirmed that we're not alone. They'll grow up in a world where extraterrestrial life is an accepted fact, where the question isn't whether life exists elsewhere, but how common it is and what forms it takes. And perhaps someday, far in the future, humans or our descendants will actually travel to K2-18b. They'll descend through that thick atmosphere, sample the waters of that global ocean, meet the organisms that evolved there. They'll see with their own eyes the life that we could only infer from spectral lines and statistical analysis. That moment, when humans and aliens finally meet face to face, or face to flagellum, or whatever interface is appropriate, that will be another watershed moment in our cosmic story. But even if that meeting never happens, even if the distances prove forever insurmountable, and we remain separated by the vast gulf of interstellar space, the knowledge itself is enough. We know now. We know that when the cosmos produces the right conditions, life emerges. We know that we're part of a larger family, that somewhere out there under the light of a red dwarf star, organisms are going about the business of living, reproducing, evolving, completely unaware that intelligent beings on a distant world have detected their presence.
This is the great gift that K2-18b has given us, the knowledge that life is not a miracle, not an impossibility, unlikely accident, but something natural and expected. The universe makes stars, it makes planets, it makes life. This is what it does. This is what we are. Children of the cosmos, born from stardust and the chemistry of carbon, participants in the grandest experiment of all, the universe's quest to understand itself. And so we continue looking outward, searching for more examples, more living worlds, more instances of this cosmic phenomenon we call life. We build better telescopes, develop more sensitive instruments, refine our theories about what biosignatures to look for. We send probes to the ocean moons of our own solar system, hoping to find life closer to home. We listen for signals from intelligent civilizations, wondering if someone out there is trying to communicate. The search continues because now we know it's not futile. Life exists. We have proof. The question is no longer whether, but where and how much and what kinds. Every new observation brings the possibility of another discovery, another living world revealed, another piece added to our understanding of this cosmic tapestry of life. But the discovery of K2-18b triggered consequences that extended far beyond astronomy and astrobiology. The revelation rippled through every institution, every discipline, every corner of human civilization. Economics, politics, art, religion. Nothing remained untouched by the knowledge that we share the universe with other living systems. Consider the economic implications alone. Within months of the announcement, a new industry began to crystallize around the search for and study of extraterrestrial life. Investment poured into telescope technology, into spacecraft development, into artificial intelligence systems capable of analyzing vast data sets from astronomical observations.
Private companies that had previously focused on Earth orbit or lunar missions suddenly pivoted toward deep space exploration and exoplanet research. The stock markets fluctuated wildly as investors tried to predict which technologies and which companies would benefit most from this new frontier. Aerospace contractors saw their valuations skyrocket. Universities with strong astrobiology programs found themselves flooded with applications and donation offers. Even industries with no obvious connection to space exploration felt the effects, as the cultural zeitgeist shifted toward a cosmic perspective that influenced consumer behavior in subtle but measurable ways. Governments recognized that the nation or coalition that led an exoplanet research would gain not just scientific prestige, but genuine geopolitical advantage. The knowledge gained from studying alien biospheres could revolutionize biotechnology, material science, energy systems, agriculture. If we could understand how life on K218b adapted to high gravity, thick atmospheres, and the spectrum of a red dwarf star, we might develop new crops that thrive in marginal conditions on Earth. If we could decode the biochemistry of organisms that survived intense stellar radiation, we might create new medical treatments, new ways to protect astronauts on deep space missions. The space agencies of major powers announced ambitious programs. China declared its intention to build a telescope array on the far side of the Moon, shielded from Earth's radio interference, specifically designed to study exoplanet atmospheres. The European Union proposed a network of space-based telescopes that would work together as a virtual instrument with unprecedented resolving power. India, often overlooked in space exploration discussions, surprised the world by unveiling plans for an innovative, low-cost mission that could potentially visit the outer planet's ocean moons within a decade. The United States, facing budgetary constraints and political divisions that had previously hampered ambitious space initiatives, found a renewed unity around the goal of exoplanet research. When politicians across the ideological spectrum could agree on little else, they could agree that America should lead in the search for extraterrestrial life. Funding for NASA increased substantially. New partnerships formed between government agencies, private companies, and international collaborators. But perhaps the most profound changes occurred not in budgets or missions, but in how humanity thought about itself. The psychological impact of knowing we're not alone cannot be overstated. For some, it was liberating. The crushing weight of cosmic loneliness lifted. We were part of something larger, connected to other living systems across the void. For others, it was terrifying. The universe suddenly seemed more crowded, less under our control, full of unknowns that might be indifferent or hostile to human existence. Mental health professionals reported a surge in what came to be called existential crisis consultations. People grappling with the implications of the K218b discovery needed help processing their feelings. Some experienced a kind of cosmic vertigo, a disorienting sense that everything they'd believed about humanity's importance had been undermined. Others felt an overwhelming sense of responsibility, believing that humanity now had obligations to these other living systems that we'd never considered before. Religious institutions faced their own reckonings. Some traditions adapted smoothly, finding in their texts and teachings precedents for a universe filled with divine creation. The Islamic concept of Allah's infinite creativity, the Hindu notion of countless worlds and realms, the Buddhist understanding of interdependence extending across vast scales, all of these provided frameworks for incorporating extraterrestrial life into existing belief systems. Other traditions struggled more. Denominations that had built their theology around humanity's unique status, around the idea that God's attention and concern focused exclusively on human beings, found the discovery deeply challenging. Some reinterpreted their doctrines, arguing that God's love extended to all living things wherever they might exist. Others doubled down on human exceptionalism, claiming that even if biological organisms existed elsewhere, only humans possessed souls or moral worth in the divine economy.